Right now, while you're listening to this, there is a program running on whatever device brought you this audio. It started before you opened anything, before you tapped any icon, before you made any choice at all. It is running underneath every application you have used today. It decided which program got the processor's attention and for how long. It kept every application's memory separate from every other application's memory, so that a mistake in one could not corrupt the work of another. It controlled every interaction between software and hardware, every read from storage, every pixel drawn on the screen, every character received from a keyboard or a touch, and unless something went wrong, you probably never thought about it. That program is your operating system, and the strange thing about it, the thing that is worth sitting with for a moment, is that nobody set out to write it. There was no meeting in the 1940s where someone said, "Here is what a computer needs between its hardware and its users. Let's design it." The operating system emerged, piece by piece, across 7 decades, built by people solving problems that had never existed before. Each solution created the next problem. Each generation of computers demanded something the previous generation's software could not provide. And the decisions those people made, under pressure, often with incomplete understanding of what they were building, are still embedded in the device you are using tonight. They are still shaping what your software can and cannot do, what is fast and what is slow, what is safe and what is vulnerable, right now, as you listen. Tonight we are going to follow that entire story, from the first machines that had no operating system at all, through the invention of every major idea that your operating system uses today. We will move slowly, because there is no rush. These systems have been running underneath everything for a long time, and they are not going anywhere. And along the way, we will build a picture of what an operating system actually does, not as a list of features, but as a set of answers to problems that real people encountered when they tried to share a machine. Let's start at the beginning, which is a room full of very expensive hardware and a long line of people waiting to use it. In the late 1940s and through the 1950s, a computer was not a device you owned. It was a room. Sometimes it was several rooms. It weighed thousands of kilograms. It cost hundreds of thousands or millions of dollars, and there might be 1 or 2 of them at an entire university or corporation. The people who used these machines were not called users. They were called programmers, or sometimes operators, and they interacted with the computer in a way that would seem unrecognizable today. Here is how it worked. You wrote your program by hand, on paper, working out the instructions in machine language or assembly language. Then you transferred those instructions onto a physical medium the computer could read. In the early days, this often meant punched cards, stiff rectangular cards with holes punched in specific positions, each pattern of holes representing an instruction or a piece of data. A typical program might fill a deck of dozens or hundreds of these cards. You carried your deck to the computer room, handed it to an operator, and waited. The physical process of preparing a program was more involved than it might sound. You started at a key punch machine, a device with a typewriter keyboard that stamped holes into blank cards. Each card held 80 columns, and each column could represent one character. You typed your program line by line, and the machine punched the corresponding holes. If you made a mistake, you threw that card away and punched a new one. When you were done, you had a stack of cards held together with a rubber band, and the order of the cards mattered. Dropping your card deck on the way to the computer room was a small disaster. Hundreds of cards scattered across the floor, and you had to reassemble them in the correct sequence before the program could run. Programmers sometimes drew a diagonal line across the top edge of a card deck with a felt pen, so they could see at a glance whether the cards were in order. The operator loaded your card deck into a card reader, which fed the cards into the machine one at a time. The computer read your program, executed it, and produced output, usually on a printer or another set of punched cards. Then the operator unloaded your job, loaded the next person's card deck, and the cycle repeated. The turnaround time, the gap between submitting your job and receiving the results, could be hours. At a busy installation, it might be a full day. If your program had a bug, a misplaced instruction, a wrong address, you would not discover the error until your printout came back. Then you fixed the error, punched a new card, put the corrected card into the right position in the deck, and submitted the whole thing again. Another wait, another day, sometimes. This was called batch processing, and the first thing to understand about it is how much time it wasted. Between one job ending and the next job beginning, the computer sat idle. The operator had to physically remove one deck, load another, set up whatever configuration the next job required, and start the machine again. Those minutes of idle time were enormously expensive, because the machine itself was enormously expensive. A minute of computer time in the 1950s could cost what a person earned in a day, and the machine spent a meaningful fraction of its day doing nothing while a human being shuffled cards. This is the problem that produced the first operating systems, though nobody called them that at the time. The question was simple and economic. How do you keep an expensive machine busy? In 1956, two programmers solved this problem in a direct and practical way. Robert Patrick, working at General Motors Research, and Owen Mock, at North American Aviation, wrote a program for the IBM 704 that automated the transition between batch jobs. Instead of waiting for a human operator to load the next job, the machine could read a sequence of jobs from a tape, execute them one after another, and move to the next job automatically when the previous one finished. They called it GM-NA-IO, and it was, by most accounts, the first operating system. What GM-NA-IO did was modest by any modern standard. It managed input and output operations and automated the job-to-job transition. It did not multitask. It did not manage memory in any sophisticated way. It did not provide a user interface, but it solved the immediate problem. The computer stopped sitting idle between jobs, and in doing so, it established a principle that would define every operating system that followed. The purpose of the operating system is to make better use of the hardware than a human being alone can manage. Some version of GM-NA-IO ran on roughly 40 IBM 704 installations. Other groups wrote similar monitor programs for their own machines. By the late 1950s, the idea that a computer should have a resident program managing the flow of work was becoming standard practice. The user group, called Share, formed by IBM 704 customers, developed the Share operating system in 1959 as an improvement on GM-NA-IO. The concept was spreading. These early monitor programs also introduced something that would become increasingly important as operating systems matured: the idea that the computer should protect itself from the programs it ran. If a user's program contained a bug that caused it to loop forever, it would occupy the machine indefinitely, preventing every other job in the queue from running. So the monitors added timers. If a program ran longer than its allocated time, the monitor interrupted it, printed a message indicating that the time limit had been exceeded, and moved on to the next job. This was the first crude form of resource management, the operating system limiting what a program could consume so that the machine remained available for everyone. Another early innovation was spooling, which stood for Simultaneous Peripheral Operations Online. The idea was to separate the input and output operations from the computation itself. Instead of reading cards directly into the processor and printing output directly from the processor, the system would read cards onto a fast magnetic tape or drum in the background, and the processor would read from that intermediate storage. Similarly, output would be written to the intermediate storage first, and the printer would print from there at its own pace, without holding up the processor. Spooling let the processor work on the next job while the printer was still finishing the output from the previous one. It was an early form of the buffering and asynchronous processing that modern operating systems use everywhere. There is another piece of the foundation laid in these years that deserves attention because it changed the fundamental relationship between the processor and everything attached to it. That piece is the hardware interrupt. In the earliest machines, when the processor needed to know whether a device had finished an operation, it asked, it checked again. This is called polling, and the problem with it is obvious. While the processor is spending its time asking a tape drive whether the tape drive is done, the processor is not doing anything useful. Polling is a busy wait, like standing at a window watching for a delivery truck instead of doing something else until the doorbell rings. The interrupt changed that. An interrupt is a signal from a hardware device to the processor that says, in effect, I need your attention now. The processor does not have to ask. When the tape drive finishes a read operation, it sends an interrupt. When a key is pressed on a terminal, the keyboard controller sends an interrupt. When a timer expires, the timer sends an interrupt. The processor, which was in the middle of executing some program's instructions, stops what it is doing, saves enough state to resume later, and jumps to a piece of code called an interrupt handler that deals with whatever the device needs. This mechanism is so fundamental to modern computing that it is easy to forget someone had to design it. The idea appeared in several machines in the late 1950s, and by the time the System 360 arrived, hardware interrupts were a core part of the architecture. They are the reason your operating system can respond to a keystroke instantly, even when the processor is busy with something else. They are the reason a network packet arriving at your machine gets processed promptly. Every interaction between the operating system and the hardware runs through interrupts, thousands of them per second, each one briefly diverting the processor to handle an event and then returning it to whatever it was doing before. Without interrupts, multiprogramming would have been far less efficient, because the processor would have spent much of its time polling devices instead of running programs. With interrupts, the processor runs programs until a device needs attention, handles the device, and goes back to running programs. The operating system's interrupt handling code is some of the most time-sensitive software on the machine. It has to run quickly, because while an interrupt is being handled, nothing else is getting done. A slow interrupt handler is a bottleneck that affects everything on the system. But batch processing, even automated batch processing, had a fundamental limitation. Only one program ran at a time. If your program needed to read data from a tape, the processor sat idle while the tape mechanism physically moved. If your program needed to write output, the processor waited while the printer printed. The input and output devices were thousands of times slower than the processor itself, and during every moment, the processor waited for a slow device. It could have been doing useful work on another program. This mismatch between the speed of the processor and the speed of everything else was not a minor inconvenience. Studies at the time showed that processors spent a significant fraction of their time waiting for input and output to complete. The machine was fast, but it was shackled to slow peripherals, and no amount of clever batch scheduling could fix that, as long as only one program ran at a time. The solution was to let multiple programs share the machine, not one after another, but simultaneously, or at least apparently simultaneously. And this idea, which seems obvious now, was genuinely difficult to implement and required solving problems that had no precedent in the history of computing. The first version of this idea was called multiprogramming. The concept was straightforward in principle. Load several programs into memory at the same time. When one program is waiting for an input or output operation to complete, switch the processor to another program that is ready to run. When that program starts waiting, switch again. The processor stays busy, bouncing between programs, doing useful work whenever any of the loaded programs has work to do. IBM implemented multiprogramming in the operating system for its System 360 family of computers, announced on April 7, 1964. This was one of the most consequential product launches in the history of technology, and the operating system was at the center of it. The System 360 was not a single computer, it was a family of computers, ranging from small machines for simple tasks to large machines for heavy computation, and they all shared a common architecture. This was the radical idea. Before the 360, IBM sold many different computer models, and each one had its own instruction set, its own peripherals, its own software. A program written for one IBM machine could not run on another IBM machine without being completely rewritten. Customers were locked into their specific model, and upgrading to a more powerful machine meant starting over. IBM spent roughly $5 billion developing the 360, an investment that, adjusted for inflation, exceeded what the United States had spent on the Manhattan Project. The bet was that customers would pay a premium for compatibility, the ability to write a program once and run it on any machine in the family, moving to a larger model as their needs grew without abandoning their existing software. The operating system for this family, called OS 360, was supposed to manage all of this. It needed to support multiprogramming, so the expensive processors would stay busy. It needed to support the full range of hardware in the family, from small installations to large ones. It needed to handle input and output devices from many manufacturers, and it needed to work reliably, because businesses were going to depend on it for payroll, inventory, accounting, and every other critical function. OS 360 fell years behind schedule. The project involved thousands of programmers, and the complexity of coordinating their work proved far greater than anyone had anticipated. Fred Brooks, who managed part of the effort, later wrote a book about the experience called The Mythical Man Month, published in 1975. The central insight of the book was that adding more programmers to a late software project makes it later, because the communication overhead between programmers grows faster than the useful work they can produce. Brooks called this observation a law, and it became one of the most widely cited ideas in software engineering. Brooks also described something he called the second system effect. A team that has successfully built a small, elegant first system will, when given the chance to build a second one, over-design it. They add every feature they wished they had the first time around, every elegant generalization they can think of, every option that any user might want. The result is a bloated, late, often barely functional system. OS 360 was, in Brooks's telling, a textbook second system effect. It tried to be everything for everyone, and the cost of that ambition was years of delays and a system that shipped with known bugs that took years more to resolve. The experience of OS 360 also established something that would recur throughout the history of operating systems: the difference between the complexity of the operating system and the complexity of the applications it supported. The applications themselves were often straightforward: a payroll calculation, an inventory report. But the operating system underneath, the system that managed the sharing of the machine, the scheduling of jobs, the allocation of memory, the handling of interruptions, was orders of magnitude more complex than any individual application. This ratio, simple applications on top of a profoundly complex foundation, became the defining characteristic of operating system development. But the 360 itself succeeded enormously. The backward compatibility that IBM built into the architecture proved so durable that a program compiled for a System 360 in the 1960s can, with minor adjustments, still run on IBM mainframes being shipped today, more than 60 years later. That is an almost unprecedented span of software compatibility, and it reflects a design choice made under enormous pressure in the early 1960s that continues to constrain and enable IBM's mainframe business in the present. Now, multiprogramming solved the problem of keeping the processor busy, but it did not solve a different problem that was becoming urgent at the same time. Multiprogramming was designed for batch jobs. You still submitted your work on punched cards, and you still waited hours, or sometimes a day, for your results. You could not interact with the computer while your program was running. You could not try something, see what happened, change it, and try again. You wrote your program, submitted it, and hoped. For scientists and researchers at universities, this was maddening. They wanted to sit at a terminal and talk to the computer, to type a command, see the result immediately, type another command, and iterate. They wanted the computer to feel like a personal tool, even though it was a shared machine costing millions of dollars. This desire produced the idea of time sharing, and the person who made it real was Fernando Corbato, a professor at MIT. In the spring of 1961, Corbato and his colleagues began building what they called the Compatible Time-Sharing System, or CTSS, for MIT's IBM 709 computer. The idea was to give each user a terminal, a keyboard, and a screen, or a printer, connected to the central computer. The operating system would rapidly switch the processor's attention among the connected users, giving each one a small slice of time, cycling through all of them many times per second. Each user would perceive the machine as responding to their commands immediately, even though the processor was actually serving dozens of people in rapid rotation. Corbato demonstrated CTSS in November of 1961, and it worked. Users could log in, type commands, run programs, and see results, all in real time, all while sharing the machine with other users who were doing the same thing simultaneously. The system was compatible, in the sense that programs written for batch processing could also run interactively, so the transition did not require throwing away existing software. This was a genuinely new experience in computing. For the first time, you could sit at a terminal and have a conversation with a computer. You could experiment, you could make a mistake, see the error, fix it, and try again, all in the space of minutes instead of hours or days. The psychological effect was profound. People who used time-sharing systems described the experience as transformative. The computer stopped being a remote, impersonal processing plant and became something closer to a partner, a tool that responded to you. CTSS also introduced ideas that became foundational to every operating system that followed. It had a password system for user authentication, one of the earliest implementations of computer passwords. It had a file system that let each user store and organize their own files. It had a command language that users typed at the terminal to interact with the system. These features seem so basic now that it is hard to imagine a time when they did not exist, but someone had to invent each of them, and many of them were invented for CTSS. Corbato received the ACM Turing Award in 1990 for his pioneering work, organizing the concepts and leading the development of the general-purpose, large-scale, time-sharing, and resource-sharing computer systems. But CTSS was built on top of an existing machine that was not designed for time-sharing, and the team quickly ran into limitations. They needed a machine and an operating system designed from the ground up for the kind of interactive, multi-user computing they had demonstrated was possible, and so they embarked on a far more ambitious project, one that would attempt to create the ultimate time-sharing system. They called it Multics. Multics, the Multiplexed Information and Computing Service, was a joint project started in 1964 by three organizations: MIT's Project Mac, which had grown out of the CTSS work, Bell Telephone Laboratories, whose programmers were among the finest in the world, and the computer division of General Electric, which was building the hardware the system would run on. The ambitions of Multics were extraordinary. It was designed to serve an entire community of users, hundreds at a time, as a computing utility, the way an electric company provides electricity. You would plug in your terminal and use computing power the way you turn on a light, without needing to know or care how the power was generated. The system would be always available, always secure, always expandable. Multics introduced ideas that were far ahead of their time. It had a hierarchical file system, where files could be organized into directories, and directories could be nested inside other directories, forming a tree structure. This is the file organization you use on every computer today, and Multics is where it came from. It had dynamic linking, the ability to load code into memory on demand, so programs only consumed the resources they actually needed at any given moment. It had a security model based on rings of protection, where different levels of the system had different privileges, and inner rings could access things that outer rings could not. This ring-based security model is still used in modern processors and operating systems. But Multics was also enormously complex, and as the years passed, the project fell behind schedule and the costs mounted. Bell Labs, which had joined the project expecting to have a working system within a few years, grew increasingly frustrated. In 1969, Bell Labs withdrew from Multics. And that withdrawal, that moment when a group of talented programmers found themselves without a project, is one of the most consequential accidents in the history of technology. Among the Bell Labs programmers who had worked on Multics were Ken Thompson and Dennis Ritchie. Thompson, in particular, had enjoyed the interactive computing environment that Multics provided, and when Bell Labs pulled out, he found himself back on a conventional batch processing machine, missing the experience of sitting at a terminal and talking to a computer. Thompson found a little-used PDP-7 minicomputer at Bell Labs, a much smaller and simpler machine than the massive mainframe Multics ran on, and in the summer of 1969, he wrote a new operating system for it. He wrote the whole thing in about a month, working in assembly language, creating a file system, a process model, and a command interpreter. It was small, it was simple, and it worked. A colleague named Brian Kernighan gave the new system a name. Multics had been multiplexed, so this smaller, simpler system was called Unix, a pun on the idea of being a stripped-down version. The spelling eventually settled into Unix. Unix was, in many ways, the opposite of Multics. Where Multics was designed by committee across 3 organizations, Unix was created by a small group of people who understood each other's work intimately. Where Multics tried to be everything to everyone, Unix focused on being useful to its own creators. Where Multics was enormous and complex, Unix was small and comprehensible. A skilled programmer could read and understand the entire Unix system, something that was impossible with Multics, and would become impossible again as operating systems grew larger. But Unix inherited the best ideas from Multics and from the time-sharing tradition more broadly. It had a hierarchical file system, it had multi-user support, it had a powerful command line interface, a shell, that let users chain simple tools together to accomplish complex tasks. And it had a philosophy that would prove enormously influential. Do one thing well. Write programs that do one thing and do it well. Write programs to work together. These principles, sometimes called the Unix philosophy, shaped a generation of software design. In 1971, Unix was moved to a more capable machine, the PDP-11, to support text processing for the Bell Labs patent department. This gave the project institutional justification because it was now providing a service that the organization valued. By 1972, there were 10 Unix installations at AT&T. And then Dennis Ritchie did something that changed the trajectory of operating systems permanently. He created the C programming language. C grew out of an earlier language called B, which Thompson had written, and which was itself based on a language called BCPL. Ritchie added types to B, created a compiler, and produced a language that was high-level enough to write complex programs comfortably, but low-level enough to interact directly with hardware. C gave programmers fine-grained control over memory and processor operations, while freeing them from the tedious detail of assembly language, where every instruction was specific to one particular processor. In 1973, Thompson and Ritchie rewrote the core of Unix in C. This was a radical step. Operating systems had always been written in assembly language because they needed to interact intimately with the hardware, and assembly language was the only tool that provided the necessary control. By writing Unix in C, Thompson and Ritchie made the system portable. The same source code could be compiled for different processors with relatively modest effort. Moving Unix to a new machine no longer meant rewriting the entire operating system from scratch. You rewrote the small parts that were truly hardware-specific, recompiled the C code for the new processor, and most of the system came along for the ride. This portability had enormous consequences. By 1977, Unix was running on many different machines, and a retrospective paper by Ritchie reported more than 300 installations on configurations ranging from single-user machines to systems supporting dozens of simultaneous users. By 1978, there were over 600 installations. AT&T, which owned Bell Labs, was at that time a regulated telephone monopoly, and the terms of its regulation restricted it from entering the computer business. This meant AT&T could not sell Unix commercially, but it could, and did, license the source code to universities for a nominal fee. Unix spread through academia like a fire through dry grass. Computer science departments at universities around the world adopted it, taught it, modified it, and contributed improvements back. A generation of computer scientists learned their craft on Unix, and the ideas embedded in Unix became the ideas embedded in their thinking. The University of California at Berkeley became a particularly important center of Unix development. The Berkeley Software Distribution, or BSD, added networking capabilities, a faster file system, and many other improvements. BSD Unix became the foundation for much of the early Internet's infrastructure, and the people who passed through Berkeley's computer science program carried Unix knowledge and Unix sensibilities into the companies they joined and the products they built for decades afterward. Thomson and Ritchie received the ACM Turing Award in 1983 for their work on Unix. The citation praised them for developing generic operating systems theory, and specifically for the implementation of the Unix operating system. There is a detail about how Unix spread through universities that helps explain why its influence was so lasting. AT&T licensed the source code, the actual text of the programs that made up Unix, not just the compiled versions that ran on machines. This meant that professors could assign their students to read the operating system itself. They could study how it worked, line by line. They could modify it, experiment with it, break it and fix it. Learning an operating system from its source code produces a different kind of understanding than learning one from a manual. You do not just learn what the system does, you learn why the designers made the choices they did, and you see the trade-offs and compromises that shaped those choices. A generation of operating system designers learned their craft by reading Unix source code at universities, and the patterns they absorbed showed up in everything they built afterward. The University of California at Berkeley deserves special mention. A graduate student named Bill Joy, who would later co-found Sun Microsystems, led the development of the Berkeley software distribution, adding virtual memory, networking support using the TCP/IP protocols that the Internet would run on, and a faster file system. The BSD networking code became the foundation of the early Internet's infrastructure, and its influence extended far beyond Unix. The networking code that Apple uses in macOS and iOS descends from BSD. The PlayStation gaming consoles run an operating system descended from FreeBSD, itself descended from Berkeley's work. BSD's networking code shaped how most operating systems implement Internet connectivity, even ones that have no other connection to Unix. The spread of Unix also created a problem that would become familiar in operating system history: fragmentation. Different organizations modified their copies of Unix to suit their own needs, and those modifications diverged. AT&T developed its own official version, System V. Berkeley developed BSD. Other vendors, Sun Microsystems, Hewlett-Packard, Digital Equipment Corporation, IBM, each produced their own variants with their own extensions. Programs written for one version of Unix did not necessarily run on another without modification. A developer who wrote an application for Sun's Solaris could not simply copy it to HP UX or IBM's AIX and expect it to work without changes. The resulting competition, sometimes called the Unix Wars, consumed much of the late 1980s and early 1990s. The industry tried to resolve the fragmentation through standardization. The IE produced a set of standards called POSIX, the Portable Operating System Interface, starting in 1988. POSIX defined a common interface that all Unix-like systems could implement, so that a program written to the POSIX standard would be portable across compliant systems. The Open Group later produced the Single Unix Specification, and the right to use the name Unix itself became a matter of trademark and certification rather than lineage. Any operating system that passed the certification tests could call itself Unix, regardless of whether it shared any source code with the original. There was also a legal dimension. In 1992, Unix System Laboratories, which AT&T had spun off to manage Unix licensing, sued Berkeley Software Design and the University of California over the BSD code. The lawsuit claimed that BSD still contained proprietary AT&T code. The case dragged on for 2 years before being settled in early 1994, and the settlement confirmed that most of the BSD code was free to use. But the 2 years of legal uncertainty slowed BSD's adoption at a critical moment, just as Linux was gathering momentum. Some historians of open-source software have argued that the lawsuit inadvertently helped Linux succeed, because developers who might have chosen BSD were reluctant to build on code whose legal status was in question. The fragmentation weakened Unix's position in the market, just as personal computers were becoming powerful enough to challenge mini-computers and workstations. Now, to understand what happened next in the story of operating systems, we need to understand what an operating system actually does, because as operating systems grew more complex, the ideas inside them became more clearly defined. The concepts that the earliest systems discovered by accident became, over time, deliberate architectural choices, and those choices determine how your device works tonight. Let's start with the most fundamental piece, the kernel. The kernel is the core of the operating system. It is the program that runs with the highest privilege level on the processor, the program that all other programs depend on but cannot directly access. The kernel sits between the hardware and everything else. When an application needs to read a file from storage, it does not talk to the storage device directly. It asks the kernel. When an application needs to send data over a network, it asks the kernel. When an application needs more memory, it asks the kernel. The kernel is the intermediary for every interaction between software and hardware. Why does the kernel exist as a separate, privileged layer? Because without it, every program would need to manage hardware directly, and any mistake in any program could crash the entire machine or corrupt another program's data. The kernel exists to enforce boundaries. It decides which programs can access which resources, how much memory each program receives, and how much processor time each program gets. It is, in a sense, the government of the computer, the authority that makes and enforces the rules that let multiple programs coexist on shared hardware. The way programs communicate with the kernel is through system calls. A system call is a controlled gateway between an ordinary program and the privileged kernel. When a program needs a service that only the kernel can provide, it makes a system call, which triggers a switch from the program's normal, unprivileged execution mode into the kernel's privileged mode. The kernel performs the requested operation, checks that the program has the necessary permissions, and returns the result. Then the processor switches back to the program's normal mode, and the program continues. This switching between modes happens constantly and rapidly. Every time a program reads a file, writes a file, opens a network connection, allocates memory, creates a new process, or does almost anything that involves hardware or shared resources, it makes one or more system calls. The switching is so fast that programs are not aware of it in any meaningful way, but it is the mechanism that keeps the system safe. The program never touches the hardware directly. It always goes through the kernel, and the kernel always checks before granting access. There is a debate in operating system design that runs through the entire history of kernels and is still not fully resolved. The question is, how much the kernel should contain. In a monolithic kernel, everything the operating system needs to do, process management, memory management, file systems, device drivers, networking, all of it runs inside the kernel, in the same address space, at the highest privilege level. This is how Unix was built. It is how Linux is built today. The advantage is speed. When one part of the kernel needs to communicate with another part, it can do so directly, because they share the same memory space. The disadvantage is risk. A bug in any part of the kernel, a faulty device driver, a mistake in the file system code, can corrupt the entire kernel and crash the machine. The alternative is a microkernel, where the kernel itself is stripped down to the absolute minimum: process scheduling, inter-process communication, and basic memory management. Everything else, drivers, file systems, networking, runs as separate user mode processes, communicating with the kernel and with each other through message passing. The advantage is robustness. If a device driver crashes, it crashes in its own process, and the rest of the system can potentially recover. The disadvantage is performance. All that message passing between separate processes takes time, and a microkernel system can be noticeably slower for operations that require frequent communication between components. The Mac kernel, developed at Carnegie Mellon University in the 1980s, was the most influential microkernel project. It demonstrated the concept clearly, but it also demonstrated the performance costs. Mac became the foundation for several commercial systems, most notably the NeXT operating system that Steve Jobs built at Next, and through NeXT, it lives on inside macOS and iOS today, though Apple's implementation is a hybrid that runs many components in kernel space for performance reasons. In practice, most successful operating systems today are either monolithic or hybrid. Pure microkernels have found their strongest foothold in embedded and real-time systems, where reliability is more important than raw throughput. The debate continues in academic computer science, but the market largely chose the pragmatic middle ground. Now let's talk about one of the kernel's most important jobs, which is managing processes. A process is a running program, not the program as it exists on your storage device, which is just a file containing instructions, but the program in action, loaded into memory, executing instructions, consuming processor time, and other resources. When you open an application on your device, the operating system creates a process for it. That process gets its own section of memory, its own accounting of resources, its own identity within the system. If you open the same application twice, you have two processes, each with its own memory and its own state, even though they are running the same underlying program. Managing processes is the operating system's most visible job. Your device right now is probably running dozens or hundreds of processes simultaneously. The web browser or media player bringing you this audio is one process. The clock updating in the corner of your screen is another. Background services checking for email, synchronizing files, monitoring your network connection, updating software, all of them are separate processes, all running at the same time, all sharing the same processor and memory. But here is the thing about simultaneously. If your device has, say, 4 processor cores, it can genuinely execute 4 instructions at the same exact moment. But there are far more than 4 processes running. So the operating system performs a continuous act of management called scheduling. It divides time into tiny slices, typically a few milliseconds each, and assigns each slice to a process. The processor executes one process for a few milliseconds, then switches to another, then another, cycling through all the processes that need attention. The switching happens so quickly that every process appears to be running continuously, even though each one is actually running in brief, interrupted bursts. The scheduler is one of the most carefully designed components of any operating system, because its choices directly affect how responsive the system feels. If the scheduler gives too much time to one process, other processes feel sluggish. If it switches too frequently, the overhead of switching consumes time that could have been spent doing real work. Modern schedulers use sophisticated algorithms to balance fairness, responsiveness, and efficiency, and different operating systems make different trade-offs. A server operating system might prioritize throughput, finishing as much total work as possible. A desktop or phone operating system might prioritize latency, making sure that the application the user is interacting with responds instantly, even if background tasks have to wait. The act of switching from one process to another is called a context switch, and it involves saving everything about the current process's state, which registers contain which values, where the process was in its execution, what memory it was using, and then loading the saved state of the next process. This has to happen in a tiny fraction of the time slice itself, or the overhead would consume too much processor time. Modern processors have hardware features specifically designed to make context switches faster, because the operating system performs them thousands of times per second. There is a deeper concept here that is worth pausing on, because it explains something fundamental about how your device works. Each process believes it has the processor to itself. The program's code does not contain instructions for sharing time with other programs. It just runs, executing one instruction after another, as if it were the only program in the world. The operating system creates this illusion by rapidly switching the processor among processes, saving and restoring their states so seamlessly that no process is aware of the interruptions. This is the same illusion that Corbato created with CTSS in 1961, each user believing they had the machine to themselves. The idea survived because it is a remarkably clean abstraction. Programs are simpler to write when they do not have to worry about sharing the processor. The complexity of sharing is hidden inside the operating system, where it can be engineered carefully, tested thoroughly, and improved without changing the programs that run on top of it. There is a related concept that came later in the history of operating systems, but has become essential to modern software: the thread. A thread is a lighter-weight unit of execution that runs inside a process. Where a process has its own memory space, its own file descriptors, and its own identity, threads within the same process share all of those resources. They share the same memory, the same open files, the same everything. What each thread gets separately is its own execution context, its own position in the code, its own stack of function calls. The advantage of threads is efficiency. Creating a new process is expensive because the operating system has to set up a complete separate environment. Creating a new thread within an existing process is cheap because most of the environment is already there. And threads within the same process can communicate by simply reading and writing shared memory, which is far faster than the mechanisms processes use to communicate with each other. The disadvantage of threads is that the shared memory, which makes them fast, also makes them dangerous. If two threads try to modify the same piece of data at the same time, the result depends on the exact timing of the processor's switches between them, and that timing is unpredictable. This category of bugs, called race conditions, is among the most difficult in all of software engineering to find and fix. The bug might appear only under specific timing conditions that occur rarely, making it almost impossible to reproduce reliably. An application might run correctly 1,000 times and fail on the 1,001st, because the threads happen to interleave their operations in a slightly different order. Operating systems provide tools to help programmers manage this problem. Mutexes, semaphores, and other synchronization primitives let threads coordinate their access to shared resources, ensuring that only one thread modifies a piece of data at a time. But using these tools correctly is itself a challenging task, and mistakes in synchronization are a major source of software defects in multi-threaded programs. Now let's talk about memory, because the operating system's management of memory is just as important as its management of processes, and the history of how this was figured out involves one of the most elegant ideas in all of computing. When a program runs, it needs memory. Not just storage on a disk, but fast, immediately accessible memory that the processor can read from and write to at full speed. This is what people commonly call RAM, random access memory, and every program needs some of it. The program's instructions are loaded into memory. The data the program is working with lives in memory. Temporary calculations, variables, the call stack that tracks which function called which other function, all of it sits in memory while the program runs. When you have only one program running, managing memory is simple. Give the program all the memory it needs, starting at a known address, and let it work. But the moment you have multiple programs running simultaneously, memory management becomes a difficult coordination problem. Each program needs its own region of memory. No program should be able to read or write another program's memory, because that would be a catastrophic security and stability failure, and the total memory demanded by all running programs might exceed the physical memory installed in the machine. The first part of this problem, keeping each program's memory separate, was solved by a concept called virtual memory, and the history of virtual memory begins with the Atlas computer. In the late 1950s, Tom Kilburn and his team at the University of Manchester in England were building a new computer called Atlas. They faced a practical problem. The fast main memory of the computer which used magnetic cores, was expensive and limited. The drum storage attached to the computer was much larger but much slower. Programmers had to manually manage the movement of code and data between the fast memory and the slow drum, a tedious process called overlaying that consumed enormous amounts of programmer time and introduced endless opportunities for error. Kilburn's team had an insight. What if the computer could manage this movement automatically? What if the hardware and a supervisory program could work together to create the illusion that all of the storage, fast and slow, was a single large memory? The programmer would write code as if the machine had far more fast memory than it physically possessed, and the system would quietly move pieces of code and data between the fast memory and the drum as needed, without the programmer's knowledge or involvement. They implemented this idea using a technique called paging. The system divided memory into fixed-size blocks called pages. At any moment, some pages were in the fast main memory, and others were stored on the drum. When a program tried to access a page that was not currently in main memory, the hardware detected this and interrupted the program. The supervisory software then fetched the needed page from the drum, placed it in main memory, possibly evicting another page that had not been used recently to make room, and restarted the program's instruction. The program was not aware that any of this had happened. It simply continued executing as if the page had been in main memory all along. Working prototypes of paging were running by 1959, and the Atlas computer became operational in 1962. The IRIGI recognized it with a milestone citation for the invention of virtual memory, covering the years 1957 to 1962. The idea spread rapidly. Within a few years, virtual memory with paging became a standard feature of large computer systems, and today it is used by essentially every general-purpose operating system on every general-purpose computer in the world. What makes virtual memory elegant is the abstraction it provides. Each process on your device right now believes it has access to a large, contiguous block of memory that starts at address 0 and extends as far as the process needs. This is a fiction. The physical memory of your device is shared among dozens or hundreds of processes, and the pieces of any one process's memory might be scattered across physical memory in no particular order. The operating system maintains a mapping, a page table, that translates each process's virtual addresses into the physical addresses where the data actually resides. The processor's hardware, a component called the memory management unit, performs this translation automatically on every memory access, so quickly that the process never perceives any delay. This gives the operating system tremendous flexibility. It can place a process's pages anywhere in physical memory, rearranging them as needed. It can give each process the illusion of having far more memory than physically exists, because not all pages need to be in physical memory at the same time. Pages that have not been accessed recently can be moved to a swap area on the storage device, freeing physical memory for pages that are actively being used. If the process later accesses a swapped-out page, the system brings it back into physical memory, possibly swapping out a different page to make room. The process never knows the difference. And the page table provides security, because each process has its own page table, and the operating system controls what entries each table contains. A process can only access physical memory that the operating system has mapped into its virtual address space. It literally cannot see or touch another process's memory, because the translation mechanism does not provide any path from one process's virtual addresses to another process's physical memory. This is not a software convention. It is enforced by the hardware itself. A misbehaving program cannot break through this barrier, because the barrier exists at the level of the processor's memory management unit. So virtual memory accomplishes three things at once. It gives each process a clean, simple view of memory, starting at 0 and extending as far as needed. It lets the operating system manage physical memory efficiently, placing pages wherever there is room. And it isolates processes from each other, preventing one process from corrupting another's memory. All three properties emerged from the same mechanism, and all three are essential to how your device operates right now. There is one more thing about memory management that is worth explaining. because it comes up whenever your device starts running slowly and you wonder why. When the operating system needs to bring a page into physical memory and there is no free space, it has to choose an existing page to evict. The choice of which page to evict is made by a page replacement algorithm, and the choice matters because it directly affects how often the system has to go to the storage device, which is slow compared to reading from memory. The ideal algorithm would evict the page that will not be needed for the longest time in the future. This optimal strategy was described mathematically by a researcher named Laszlo Bilaty in 1966. The problem, of course, is that the operating system does not know the future. It cannot know which page will be needed next, so it has to guess based on the past. The most common practical approximation is called least recently used, which evicts the page that has not been accessed for the longest time. The logic is simple. If a page has not been touched recently, it is probably not going to be touched soon. This is not always true, but it works well enough for most workloads. When too many programs are running and the physical memory is badly oversubscribed, the system can fall into a state called thrashing. In thrashing, the operating system spends most of its time moving pages in and out of memory, and very little time doing actual useful work. Every time it brings one page in, it has to evict another page that some process will need almost immediately, and the constant swapping overwhelms the system. Your device slows to a crawl, the storage light blinks continuously, and everything takes far longer than it should. The operating system detects this condition and tries to mitigate it, sometimes by suspending processes to reduce the demand on physical memory, but the fundamental solution is either to close some applications or to have more physical memory installed. Let's move to file systems, because the other side of memory management is persistence. RAM is fast but temporary. When you turn off your device, everything in RAM is gone. If you want data to survive, you need to write it to storage, a hard drive, a solid-state drive, a flash chip, whatever persistent medium your device uses, and the file system is how the operating system organizes data on that storage. The concept of a file seems so natural that it is easy to forget it was invented. In the earliest computers, there were no files. There were tapes and card decks and drum tracks, and the programmer kept track of where things were stored through manual accounting. The idea that data on a storage device should be organized into named units, grouped into named containers, arranged in a hierarchy that people can navigate by name, that was a design decision, and it came largely from the time-sharing era. Multics introduced the hierarchical file system, where files lived inside directories, and directories could be nested inside other directories, forming a tree. Unix adopted and refined this idea, and it added something distinctive. In Unix, everything was a file. Not just documents and programs, but hardware devices, network connections, running processes, all of them could be accessed through the file system, using the same operations, open, read, write, close, that you would use on an ordinary file. A printer was a file. A terminal was a file. The system's own internal state could be examined by reading files in special directories. This everything is a file philosophy was a powerful simplification. It meant that tools designed to work with files could be applied to almost anything in the system. You could redirect the output of a program to a file, to a printer, or to another program using the same mechanism. The uniformity reduced the number of concepts a programmer needed to learn and increased the number of ways that tools could be combined. Under the surface, a file system manages an enormous amount of bookkeeping. It tracks which blocks on the storage device belong to which file. It manages the free space on the device, knowing which blocks are available for new data. It maintains metadata for each file, the name, the size, the timestamps recording when the file was created, modified, and last accessed, the permissions controlling who can read or write or execute the file. In the Unix tradition, this metadata is stored in a structure called an inode. Each file has an inode, and the inode contains everything the system needs to know about the file except its name. The name is stored separately in the directory that contains the file. This separation might seem odd, but it enables a useful feature. The same inode, the same file, can have multiple names in multiple directories. These multiple names are called hard links, and they all point to the same underlying data. The file is not truly deleted until the last link to its inode is removed, and no process has the file open. Different operating systems developed different file system designs with different trade-offs. The FAT file system, file allocation table, was used on early personal computers starting in the late 1970s. It was simple and well understood, which made it widely compatible, but it lacked features like permissions and journaling. Microsoft replaced it with NTFS, the New Technology File System, in 1993, adding security permissions, journaling for crash recovery, encryption, and compression. Apple's file systems evolved through HFS, HFS+, and eventually APFS, each generation adding features that the previous one lacked. Journaling deserves a moment of explanation because it addresses a problem that is easy to overlook. When the operating system writes data to a storage device, the write might involve multiple separate updates. Creating a new file might require updating the free space map, writing the file's data to blocks on the device, creating an inode with the file's metadata, and adding an entry in the directory. If the power fails or the system crashes in the middle of this sequence, the file system could be left in an inconsistent state, with some updates completed and others missing. A journaling file system writes a record of what it intends to do before it does it. If the system crashes, it can read the journal when it restarts and either complete the interrupted operation or undo it cleanly, bringing the file system back to a consistent state. There is another function of the operating system that is easy to overlook because it happens invisibly, but without it, most useful software would not work. That function is inter-process communication, the mechanisms that let separate processes talk to each other. Processes, as we discussed, are isolated from each other. Each one has its own memory space, and one process cannot read or write another process's memory. This isolation is essential for security and stability, but it creates a problem. Sometimes processes need to cooperate. A web browser needs to send a request to a network service running in a different process. A word processor needs to send a document to a print spooler. A video player needs to receive data from a download manager. The operating system provides several mechanisms for this communication. The simplest is the pipe, an idea that originated in Unix. A pipe is a one-way channel that connects the output of one process to the input of another. When you type a command like list all files and filter the results, you are creating a pipe between two programs. The first program writes its output into the pipe, and the second program reads from it, as if the pipe were a file. The operating system manages the buffering and the synchronization, ensuring that the reading process waits if there is nothing to read, and the writing process waits if the buffer is full. Pipes are simple and elegant, but they only work between processes that know about each other and that are set up to communicate in advance. For more flexible communication, operating systems provide other mechanisms. Sockets, which were developed as part of the BSD networking work at Berkeley, allow two processes to communicate as if they were sending messages across a network, even if both processes are running on the same machine. Shared memory lets two processes map the same region of physical memory into both of their address spaces, so that writes by one are immediately visible to the other. Message queues let processes send structured messages to a queue that the receiving process reads at its own pace. Each of these mechanisms involves trade-offs between speed, flexibility, and complexity. Shared memory is the fastest because no copying is involved, but it requires careful synchronization to avoid the same race conditions that plague threads. Sockets are the most flexible because they work identically whether the processes are on the same machine or on different machines across a network, but they have more overhead. Pipes are the simplest, but they are limited to one-way communication between two processes. Now let's talk about something that sits between the kernel and the hardware, a layer that most people never think about, but that makes modern computing possible: device drivers. Your computer or phone contains hardware from many different manufacturers. The processor might be made by one company, the graphics chip by another, the wireless radio by a third, the storage controller by a fourth. Each piece of hardware has its own design, its own commands, its own way of communicating with the rest of the system. Without some kind of translation layer, the operating system would need to contain specific code for every possible piece of hardware it might encounter, from every manufacturer, in every variation. That would be impractical. The combinations are too numerous, and the hardware changes too quickly. Device drivers solve this problem. A device driver is a piece of software, usually written by the hardware manufacturer, that translates between the operating system's generic requests and the specific commands that a particular piece of hardware understands. The operating system says, "Write this data to the storage device." The driver translates that request into the specific sequence of commands that this particular storage controller from this particular manufacturer expects. The operating system says, "Display this image on the screen." The graphics driver translates that request into the specific instructions that this particular graphics chip requires. From the operating system's perspective, every storage device looks the same. Every graphics chip looks the same. Every network adapter looks the same. The drivers provide a uniform interface, hiding the differences behind a standardized set of commands. This is sometimes called a hardware abstraction layer, and it is one of the reasons that modern operating systems can run on an enormous variety of hardware without being rewritten for each new device. The driver model also explains why new hardware sometimes does not work with older operating systems, or why a new operating system might initially lack support for certain hardware. If the manufacturer has not written a driver for that operating system, the system cannot communicate with the hardware, regardless of whether the hardware is physically capable of working. The hardware exists in its own world. The operating system exists in its world. The driver is the bridge between them, and without the bridge, neither side can reach the other. There is one more piece of the operating system's infrastructure that deserves its own discussion, because it is the reason your device can communicate with the rest of the world. That piece is the networking stack. When your device connects to the internet, it does not simply send raw data out through a wire or a radio. It packages that data according to a set of protocols, standardized rules that govern how information is formatted, addressed, transmitted, received, acknowledged, and reassembled at the other end. The operating system implements these protocols in a layered stack, where each layer handles one aspect of communication and passes data to the layer above or below it. At the bottom of the stack is the network interface, the physical hardware that sends and receives electrical signals, radio waves, or light pulses. Above that sits the data link layer, which handles the immediate, hop-by-hop delivery of data across a local network. Above that is the network layer, which handles routing, figuring out how to get data from your machine to a destination that might be on the other side of the world. This is where the Internet Protocol, or IP, operates, assigning addresses to machines and routing packets between networks. Above the network layer is the transport layer, which ensures reliable delivery. The most commonly used transport protocol is TCP, the Transmission Control Protocol. TCP takes the data your application wants to send, breaks it into segments, numbers them, sends them, waits for acknowledgements, retransmits anything that gets lost, and reassembles the segments in order at the destination. All of this happens inside the operating system's kernel, invisible to the application that asked to send the data. The application interacts with this entire stack through sockets, the same socket interface that was developed at Berkeley in the early 1980s as part of the BSD Unix networking work. A socket is an endpoint for communication, and the programming interface for sockets is remarkably simple. Create a socket, connect it to a destination, send data, receive data, close it. Behind that simple interface, the operating system is performing a vast amount of work, segmenting data, computing checksums, managing retransmissions, handling congestion, routing packets through a global network of interconnected routers. The networking stack is now one of the largest and most complex components of any operating system. It handles not just the basic protocols, but also wireless connectivity, Bluetooth pairing, VPN tunneling, firewall rules, quality of service management, and dozens of other functions. Every time you load a page, stream a video, or receive a notification, the operating system's networking stack is doing the work of turning your application's simple request into the correct sequence of protocol operations across multiple layers. Let's talk about permissions and security, because once you have multiple users sharing a machine or multiple applications sharing a device, you need rules governing who can do what. The earliest time-sharing systems, including CTSS, introduced passwords to verify user identity, but authentication, confirming that you are who you claim to be, is only the beginning of security. The deeper question is authorization, determining what an authenticated user is allowed to do. Unix established the permissions model that still underlies most operating systems today. Every file in a Unix system has an owner and a group, and every file has 3 sets of permissions, one for the owner, one for members of the group, and one for everyone else. Each set specifies whether that category of user can read the file, write to the file, or execute the file. These 9 bits, 3 permissions for each of 3 categories, are simple and compact, but they provide enough granularity for most situations. The Multics ring-based protection model added another layer. Instead of treating all privileged code as equally trusted, Multics arranged the system into concentric rings, with the innermost ring having the most privilege and the outermost having the least. The kernel operated in the innermost ring. Utility programs operated in intermediate rings. User applications operated in the outermost ring. Each ring could access services provided by inner rings, but inner rings were protected from outer rings. Modern processors still implement a version of this model. The kernel runs in what is typically called ring 0 or kernel mode, and applications run in a less privileged mode, sometimes called user mode. The hardware enforces the boundary. A program running in user mode cannot execute certain instructions or access certain memory regions that are reserved for kernel mode. If it tries, the processor raises an exception and the operating system handles the violation, usually by terminating the offending process. This hardware-enforced separation is the foundation of everything else in operating system security. Without it, any program could reach into the kernel's memory, modify the kernel's code, and take control of the entire machine. With it, programs are confined to their own sandboxes, and the only way to access restricted resources is through the system calls the kernel provides, where every request can be checked against the permission rules. Now let's step back into history and follow what happened when computers became personal. Through the 1960s and early 1970s, computers were institutional machines. They lived in air-conditioned rooms at universities, corporations, and government agencies. The idea that an individual person would own a computer was, to most people in the industry, absurd. Computers were large, expensive, and required teams of specialists to operate. Why would an individual need one? The answer came from an unexpected direction. In the late 1960s and into the 1970s, the price and size of electronic components dropped dramatically. The integrated circuit, which packed many transistors onto a single chip, made it possible to build smaller, cheaper processors. In 1971, Intel released the 4100, the first commercially available microprocessor, a complete processor on a single chip. It was designed for calculators, but it demonstrated that a processor no longer needed to be a rack of electronics. It could be a single component. The microprocessor made the personal computer possible. By the mid-1970s, hobbyists and small companies were building small computers around microprocessors like the Intel 8080 and the Zilog Z80. These machines were inexpensive, at least compared to mini-computers and mainframes, and they could sit on a desk. But they needed software, and in particular, they needed operating systems. Gary Kildall, a computer scientist and instructor at the Naval Postgraduate School in Monterey, California, wrote the operating system that filled this gap. In 1974, Kildall created CP/M, which stood for Control Program Monitor, later reinterpreted as Control Program for Microcomputers. CP/M ran on the Intel 8080 processor and provided the basic services a personal computer needed: a file system, a command line interface, and a way to load and run application programs. CP/M was not fancy. It did not multitask. It did not support multiple users. It managed a single disk drive and a single program at a time. But it was available. It was portable across different hardware that used the same processor, and it became the standard operating system for the early microcomputer industry. In the fall of 1974, in Pacific Grove, California, Kildall and an engineer named John Torode successfully booted a computer from a floppy disk drive, a milestone that the IEEE recognized with a milestone citation. By the late 1970s, CP/M was running on hundreds of thousands of machines from dozens of manufacturers. It was the first widely used personal computer operating system. Kildall incorporated digital research in 1976 with his wife Dorothy McEwen, and the company grew as CP/M became the industry standard. Application software was written for CP/M, and the ecosystem of hardware and software that grew around it laid the foundation for the personal computer industry that followed. And then IBM decided to build a personal computer. This was a momentous decision because IBM was the dominant computer company in the world, the maker of mainframes and mini-computers, the company whose name was synonymous with serious, institutional computing. For IBM to enter the personal computer market was a validation of the entire concept. It signaled that personal computers were not toys for hobbyists but legitimate business tools. IBM's PC project moved fast by IBM standards. The team, working in Boca Raton, Florida, was given unusual autonomy to build a machine quickly, using off-the-shelf components wherever possible. They chose the Intel 8088 processor and went looking for an operating system. What happened next has become one of the most told stories in technology, and the details have been debated for decades. The widely repeated version goes like this. IBM first approached digital research about licensing CP/M for the new machine, but the meeting did not go well, and no agreement was reached. IBM then turned to Microsoft, a small company in Seattle that was already contracted to provide a basic interpreter for the PC. Microsoft did not have an operating system, but a programmer named Tim Patterson at a company called Seattle Computer Products had written one. Patterson had created an operating system for the Intel 8086 processor called QDOS, which stood for Quick and Dirty Operating System. He later renamed it 86DOS. It was modeled on CP/DAM's interface, so programs written for CP/DAM could be adapted to run on it without too much difficulty. Microsoft licensed 86DOS from Seattle Computer Products in December of 1980, paying $25,000 for a non-exclusive license. They adapted it for the IBM PC's hardware. Then, in July of 1981, about 2 weeks before IBM started shipping the PC, Microsoft bought the full rights to 86DOS from Seattle Computer Products for $50,000. Microsoft renamed it MS-DOS and licensed it to IBM as PC-DOS. The IBM personal computer launched in August of 1981 with PC-DOS as its operating system. It was a success, and more importantly, its open architecture, built from off-the-shelf components, allowed other manufacturers to build compatible machines. These IBM-compatible personal computers, or clones, spread rapidly through the business world in the early 1980s, and nearly all of them ran MS-DOS because that was the operating system that IBM had chosen and that all the software was written for. MS-DOS was a command-line operating system. You interacted with it by typing commands at a blinking cursor. It did not multitask. It did not support multiple users. It had limited memory management, constrained by the architecture of the original IBM PC. But it was the foundation on which the entire IBM-compatible personal computer industry was built, and it made Microsoft one of the most important software companies in the world. Now, while all of this was happening in the world of text-based, command-line computing, a completely different idea about how people should interact with computers was being developed at a research laboratory in Palo Alto, California. The Xerox Palo Alto Research Center, universally known as Xerox PARC, was one of the most fertile research environments in the history of technology. Xerox, a company whose business was photocopiers, established PARC in 1970 to invent the future of computing. They hired brilliant people and gave them remarkable freedom, and the result was a series of inventions that defined the direction of personal computing for the next half-century. In 1973, a team at PARC, including Butler Lampson, Chuck Thacker, and Alan Kay, built the Xerox Alto. The Alto was a personal computer in the sense that it was designed for a single user, but it was not a consumer product. It cost roughly $40,000 and was intended as a research tool. What made the Alto revolutionary was its interface. The Alto had a high-resolution graphical display, 606 by 808 pixels, oriented vertically like a sheet of paper. It had a mouse, a pointing device that controlled a cursor on the screen. It had windows, rectangular areas on the screen that could display different documents or applications, overlapping each other the way papers overlap on a desk. It had icons, small graphical symbols that represented files and programs. It had menus, lists of commands that appeared when you clicked on them. None of these concepts existed in the world of command-line computing. In the command-line world, you typed text, and the computer responded with text. In the Alto's world, you pointed and clicked. You dragged things across the screen. You saw your document on screen as it would appear when printed, an idea called WYSIWYG. What you see is what you get. The Alto was also connected to other Altos through Ethernet, a local area networking technology that was invented at PARC, and it could print to a laser printer, another PARC invention. The Alto was the prototype of the modern personal computer interface. Nearly everything you see when you look at a computer screen today, the windows, the icons, the menus, the pointer, the idea of pointing and clicking rather than typing commands, was demonstrated on the Alto in 1973. And then Xerox failed to turn it into a product. The reasons for this failure have been analyzed endlessly. Xerox was a copier company. Its executives did not fully understand what they had. The Alto was expensive. The market for personal computers barely existed yet. Xerox did eventually release a commercial product based on PARC's ideas, the Xerox Star, in 1981, but it was priced at $16,500 per workstation and sold poorly. The ideas that PARC invented were commercialized by other companies. The most famous of those other companies was Apple. In November of 1979, Steve Jobs visited Xerox PARC. Apple was preparing to go public, and Xerox had been allowed to buy Apple shares before the public offering. In exchange, Apple's engineers were given a tour of PARC's technology. Jobs later described being so blinded by the first thing they showed me, which was the graphical user interface, that he thought it was the best thing I'd ever seen in my life. The visit to PARC influenced Apple's direction. The Lisa, released in January of 1983, was Apple's first computer with a graphical user interface driven by a mouse. It was expensive, nearly $10,000, and it was not a commercial success. But it proved the concept, and the team that built the Lisa's successor, the Macintosh, refined the interface into something more accessible and more affordable. The Macintosh launched on January 24, 1984, with a famous television advertisement directed by Ridley Scott that aired during the Super Bowl. The machine cost $2,495, still expensive, but within reach of more buyers than the Lisa. Its operating system, initially called System 1, presented a graphical desktop with icons, folders, and a trash can. You navigated by pointing and clicking with a mouse. You opened programs by double-clicking their icons. You organized files by dragging them between folders. You deleted files by dragging them to the trash. The Macintosh did not immediately dominate the market. Its original configuration had limited memory and no hard drive, and the IBM PC and its clones, running MS-DOS and later Windows, had a much larger software library. But the Macintosh established the graphical user interface as a viable alternative to the command line, and it demonstrated that regular people, not just programmers and hobbyists, could use a computer comfortably if the interface was designed for them. Microsoft, watching all of this, was developing its own graphical layer for MS-DOS. Windows 1.0 was released on November 20, 1985. It was not a full operating system. It was an operating environment that ran on top of MS-DOS, providing a graphical interface with tiled windows. It was, by most accounts, awkward and limited. Windows 2.0, released in 1987, improved things somewhat, adding overlapping windows instead of tiled ones. But it was Windows 3.0, released on May 22, 1990, that turned Microsoft's graphical interface into a mass-market success. Windows 3.0 sold over 3 million copies in its first year. It introduced a cleaner visual design, better memory management, and broader hardware support. Its successor, Windows 3.1, single-handedly propelled Microsoft Windows to 85% market share across all PCs by the end of 1993. The personal computer industry had chosen its platform, and that platform was Microsoft. Then came Windows 95, released in August of 1995, and it was a watershed. Windows 95 was the first version of Windows that was a full operating system rather than a graphical shell running on top of MS-DOS, though it still contained MS-DOS underneath for backward compatibility. It introduced the Start menu, the taskbar, and the desktop metaphor that hundreds of millions of people would use for the next 3 decades. It supported long file names, replacing the old 8.3 naming convention of MS-DOS. It had preemptive multitasking for programs written to its new interface, meaning the operating system could forcibly switch between programs on a schedule rather than relying on each program to voluntarily yield the processor. The launch of Windows 95 was a cultural event as much as a technology release. Microsoft spent hundreds of millions of dollars on marketing. People lined up outside stores at midnight to buy it. The Rolling Stones licensed "Start Me Up" as the theme song. It was, in a sense, the moment when operating systems entered popular consciousness. Before Windows 95, most people who used computers knew they had an operating system, but did not think about it much. After Windows 95, the operating system was a brand, a consumer product, a thing people had opinions about and loyalties toward. Windows 95's dominance cemented Microsoft's position, and over the following decades, Windows continued to evolve. Windows NT, developed in parallel since the late 1980s, under the leadership of Dave Cutler, a veteran of Digital Equipment Corporation's VMS operating system, provided the enterprise-grade foundation. Windows 2000 and Windows XP merged the consumer and enterprise lines into a single platform. Windows Vista, released in 2007, stumbled with heavy hardware requirements and user interface changes that frustrated people. Windows 7, released in 2009, was widely praised as a return to form. Windows 8 tried to bridge the gap between desktop and tablet interfaces and was largely rejected by desktop users. Windows 10, released in 2015, settled into a stable, gradually updated platform that served hundreds of millions of users for years. Each of these versions made choices, some successful and some not, about how to balance familiarity and innovation, backward compatibility and progress, security and convenience, and each of those choices was shaped by the ones that came before, going all the way back to the original decision to build a graphical shell on top of MS-DOS. Now let's talk about Linux, because the story of how a free operating system written by a student in Helsinki became the foundation of most of the world's computing infrastructure is one of the most remarkable stories in the history of technology. In 1991, Linus Torvalds was a 21-year-old computer science student at the University of Helsinki in Finland. He had a personal computer with an Intel 386 processor, and he was using Minix, a small Unix-like operating system written by Andrew Tannenbaum for educational purposes. Torvalds was not satisfied with Minix. Its license at the time did not allow users to modify the source code freely, and its design made choices that Torvalds disagreed with. So Torvalds started writing his own operating system kernel. He began in April of 1991, working in his apartment, and by the summer, he had something functional enough to share. On August 25, 1991, he posted a message to the Usenet newsgroup comp.os.minix that would become one of the most quoted announcements in computing history. "Hello everybody out there using Minix," Torvalds wrote. "I'm doing a free operating system, just a hobby, won't be big and professional like GNU, for 386, 486 AT clones." The modesty of that announcement is almost painful in retrospect. Just a hobby. Won't be big and professional. Torvalds was describing what would become one of the most consequential pieces of software ever written. Torvalds released the kernel as free software, meaning anyone could download it, read the source code, modify it, and redistribute their modifications. This was in alignment with the broader free software movement led by Richard Stallman, who had founded the GNU project in 1983 with the goal of creating a complete free operating system. The GNU project had built many of the tools needed for such a system: compilers, editors, shell programs, utilities, but it had not completed its own kernel. Torvalds's kernel filled that gap. The combination of the Linux kernel with the GNU tools created a complete, free, Unix-like operating system that anyone could use. Linux version 0.01 was released on September 17, 1991. The code was specific to the Intel x86 architecture and was not portable, but the open nature of the project attracted contributors from around the world. Programmers downloaded the source code, fixed bugs, added features, and sent their changes back to Torvalds, who reviewed them and incorporated the ones he approved. This collaborative development model, enabled by the Internet and by the open licensing of the code, allowed Linux to grow at a pace that no single company or institution could have matched. Over the following years, Linux was ported to other processor architectures. It gained networking capabilities, graphical support, and compatibility with an enormous range of hardware. Companies like Red Hat, SUSE, and Debian packaged Linux with software and services to create distributions that were practical for everyday use, and Linux found its way into places that Torvalds could not have imagined in 1991. Today, the majority of the world's web servers run Linux. The vast majority of cloud computing infrastructure runs Linux. Nearly all of the world's 500 most powerful supercomputers run Linux. The Android operating system, which powers billions of smartphones, is built on top of the Linux kernel. The routers, switches, and other networking equipment that carry your data across the internet frequently run Linux. Embedded systems in cars, televisions, medical devices, and industrial equipment run Linux. The International Space Station runs Linux on its laptops. The hobby that won't be big and professional became the operating system underneath a significant portion of human civilization's computing infrastructure, and it happened not because any company decided it should, but because the code was available to anyone, and enough people found it useful enough to contribute to, improve, and deploy. There is something worth pausing on here, because it says something important about how operating systems evolve. Linux succeeded not because it was technically superior to every alternative, though it is a genuinely well-engineered system. It succeeded because its licensing model allowed an entire community to participate in its development, and because the Internet made that participation practical. The source code traveled freely. Improvements flowed back to the central project. Bugs found by one person were fixed for everyone. The collective effort of thousands of contributors, working across decades, produced a system that no single organization could have built alone. This is a different model from the one that produced Windows or Mac OS, where a single company writes the operating system, controls the source code, and sells or licenses the product. Both models have produced excellent operating systems. But the open source model demonstrated that coordination without centralized control could produce software of enormous scope and quality, and that demonstration changed the software industry's understanding of what was possible. Now let's follow the story into your pocket, because the arrival of operating systems on mobile phones was the most recent major transformation in how operating systems are designed and used, and it happened with astonishing speed. For most of the history we have covered, operating systems ran on machines that sat on desks or filled rooms. The user sat in one place, used a keyboard and mouse or a terminal, and the computer stayed where it was. Mobile phones existed, but for decades, they ran simple embedded software, not general-purpose operating systems. A phone in the 1990s could make calls and maybe store a few contacts, but it was not a computer in any meaningful sense. That began to change in the early 2000s. Phones became more capable. They got color screens, cameras, and the ability to run small applications. Operating systems like Symbian, developed by Nokia and other companies, provided a platform for more complex software on mobile devices. Palm OS powered the Palm Pilot and its successors. BlackBerry's operating system dominated the market for business smartphones. Microsoft released Windows Mobile. These platforms treated the phone as a small computer, providing the operating system services, process management, memory management, file systems that applications needed to run. But the device that redefined what a mobile operating system could be was the iPhone, and the announcement was made on January 9, 2007, at the Macworld conference in San Francisco. Steve Jobs walked onto the stage and told the audience he was introducing 3 products: an iPod with touch controls, a revolutionary mobile phone, and a breakthrough internet communications device. He repeated the list, letting the audience's laughter build as they realized it was one product. "Are you getting it?" he asked. "These are not 3 separate devices. This is one device." The iPhone ran an operating system based on the same foundation as Mac OS X, which was itself descended from NextStep, the operating system built by Steve Jobs' company Next during the years he was away from Apple. NextStep was in turn based on the Mac microkernel and BSD Unix, so the operating system in the first iPhone was, at its root, a descendant of the Unix tradition that Thompson and Ritchie had started at Bell Labs in 1969. Apple initially described the iPhone software as running OS X, the desktop operating system adapted for a phone. The software was later given its own name, iPhone OS, and eventually shortened to iOS. What made iOS different from previous mobile operating systems was its interface. The entire screen was a touch surface. There was no physical keyboard. There was no stylus. You interacted with the device by touching the screen directly, tapping, swiping, pinching to zoom, using gestures that felt natural and intuitive. The operating system was designed from the ground up for this mode of interaction, and it set the standard that every subsequent smartphone would follow. The operating system also made choices about security and application management that were new and, depending on your perspective, either brilliant or restrictive. Applications could only be installed through Apple's App Store. Each application ran in a sandbox, isolated from other applications, with limited access to the system and to other applications' data. The operating system controlled which hardware features each application could access: cameras, microphone, location, contacts, and required the user to explicitly grant permission for each one. This permission model was a significant evolution in operating system security. Earlier operating systems generally gave applications broad access to the system once they were running. The idea that an application would have to ask the user for permission to access specific hardware or data, and that the user could deny that permission, was a departure from tradition. It reflected the reality that a phone carried far more personal data than a desktop computer: location, photographs, messages, contacts, financial information, and that giving every application unrestricted access to all of that data was an unacceptable risk. Android arrived the following year, though its story began earlier. Andy Rubin, Rich Miner, Nick Sears, and Chris White founded Android Incorporated in October of 2003 in Palo Alto, California. The company initially planned to build an operating system for digital cameras, but quickly shifted its focus to mobile phones. In 2005, Google acquired Android for $50 million. The first commercial Android device, the HTC Dream, also known as the T-Mobile G1, launched in September of 2008. It had a 3.2-inch touchscreen that slid up to reveal a physical keyboard, hedging the bet on whether people would accept a phone without physical keys. Android was built on top of the Linux kernel, which gave it the stability, security, and hardware support that the Linux community had developed over nearly 2 decades. On top of the kernel, Android added its own frameworks, its own application model, and its own user interface. But at the foundation, every Android phone is running Linux. The key difference between Android and iOS was openness. Android was open source. Any hardware manufacturer could use Android on their devices without paying a licensing fee to Google. This allowed dozens of companies, Samsung, LG, HTC, Motorola, Huawei, Xiaomi, and many others, to build Android phones at many different price points for many different markets. The result was that Android spread far more widely than any proprietary mobile operating system could have. As of the mid-2020s, Android runs on billions of active devices worldwide, more than any other operating system by device count. The smartphone transformed the operating system from something that sat on your desk to something you carried everywhere, and in doing so, it brought the operating system into intimate contact with every aspect of daily life. Your phone's operating system manages your alarm clock, your calendar, your messages, your photographs, your banking, your navigation, your health monitoring, your entertainment. It mediates your relationship with the physical world through cameras, GPS, accelerometers, and wireless radios. It makes decisions about power consumption, because a phone is battery-powered, and every processor cycle spent running costs energy and shortens the time before you need to charge. This power management is a dimension of operating system design that barely existed in the desktop era. A desktop computer is plugged into the wall. It does not run out of power. A phone must manage its energy budget carefully, dimming the screen when possible, putting the processor into low-power states when nothing is happening, limiting how much work background applications can do, and making dozens of other trade-offs between performance and battery life. The operating system makes most of these decisions without the user's awareness, balancing the desire to respond instantly when you pick up the phone against the need to still have battery remaining at the end of the day. Now let's talk about what has happened to operating systems more recently, because the story does not end with the smartphone. The role of the operating system continues to evolve, and 2 ideas in particular have changed how operating systems are used at the largest scales: virtualization and containerization. Virtualization is the idea that one physical computer can pretend to be many computers. The concept is not new. IBM explored virtualization on its mainframes as far back as the late 1960s with a system called CP/CMS that allowed multiple virtual machines to run simultaneously on the same physical hardware, each one believing it had the machine to itself. Each virtual machine had its own operating system, its own applications, its own view of the hardware, and the underlying system, called a hypervisor, managed the sharing. This idea remained mostly in the mainframe world for decades, until VMware brought it to standard personal computer hardware in 1999 with VMware Workstation. For the first time, you could run multiple operating systems simultaneously on an ordinary desktop or laptop computer, Windows running inside a window on a Mac, Linux running alongside Windows. Each virtual machine was isolated from the others and from the host system, providing a clean separation between different environments. Virtualization transformed the data center. Instead of running one operating system on each physical server, with most servers using only a fraction of their capacity most of the time, Administrators could run many virtual machines on fewer physical servers, each one fully utilizing its hardware. This reduced the number of physical machines needed, saving money on hardware, power, cooling, and physical space. Cloud computing, the idea that you can rent computing resources over the internet instead of buying and maintaining your own hardware, is built on virtualization. When you launch a server in a cloud service, you are typically getting a virtual machine running on shared physical hardware. But virtual machines carry their own overhead. Each one runs a complete operating system, with its own kernel, its own drivers, its own memory management, its own copies of all the system software. Running 10 virtual machines means running 10 copies of the operating system, each one consuming memory and processor time. Containerization offers a lighter alternative. A container shares the host operating system's kernel, but runs in an isolated environment with its own view of the file system, its own process space, and its own network identity. Containers are much smaller and faster to start than virtual machines because they do not need to boot an entire operating system. They share the kernel that is already running. The concept of containerization has its roots in earlier technologies. FreeBSD jails, introduced around 2000, allowed administrators to partition a FreeBSD system into isolated environments. Linux added features called namespaces and control groups, or C groups, that provided the building blocks for container isolation. But it was Docker, launched in 2013, that made containerization accessible and popular. Docker provided a simple way to package an application with all its dependencies into a container that could be moved between environments and would behave the same way everywhere. A developer could build a container on their laptop, test it, and then deploy the same container to a production server, confident that it would work identically. This consistency, the elimination of the "it works on my machine" problem, was Docker's key contribution. Containerization has become the standard way that large-scale internet services deploy software. A modern web application might consist of dozens or hundreds of containers, each one running a small piece of the overall service, managed by orchestration systems like Kubernetes that automatically start, stop, move, and scale containers across clusters of machines. The operating system's role in this world is different from its role on your laptop or phone. It provides the kernel, the isolation mechanisms, and the networking stack, but the applications sit in containers that are almost their own tiny environments, portable, reproducible, and disposable. There is another category of operating system that runs quietly alongside all the ones we have discussed, and it powers a surprisingly large portion of the technology you encounter every day. These are real-time operating systems, designed not for general-purpose computing, but for situations where the system must respond to events within a guaranteed time window. When you press the brake pedal in a modern car, a computer receives a signal from the pedal sensor and must send the correct command to the braking actuators within a few milliseconds. There is no acceptable delay. A general-purpose operating system like Windows or Linux makes no promises about when a particular task will get the processor's attention. It will get there eventually, probably within a few milliseconds, but probably and eventually are not acceptable when you are stopping a car at highway speed. A real-time operating system guarantees that a task of a given priority will start executing within a known, bounded time after the event that triggers it. The scheduler in a real-time system uses strict priority rules. The highest priority task always runs first, and it can interrupt any lower priority task at any moment. The kernel itself is designed so that even its internal operations can be interrupted, ensuring that the highest priority task is never waiting for the kernel to finish something less important. Real-time operating systems run in anti-lock braking systems, engine control units, medical ventilators, industrial robots, aircraft flight controllers, satellite communication systems, and the control systems of nuclear power plants. They are invisible to most people, but they are managing situations where a missed deadline is not an inconvenience, but a potential catastrophe. VxWorks, one of the most widely deployed real-time operating systems, has flown on every NASA Mars rover. QNX, another real-time system, runs in the infotainment and safety systems of millions of automobiles. These systems are a reminder that the story of operating systems is not only about desktops, servers, and phones. It is also about the invisible computers embedded in the physical world, each one running an operating system tailored to the specific demands of its task, each one quietly managing hardware, scheduling work, and enforcing deadlines in places most people never think to look. Let's pause here and take stock of where we have been, because the story of operating systems is really a story about a single question asked over and over in different forms. How do you share a machine? The first answer was batch processing, one program at a time, managed by an operator, later managed by a monitor program that automated the transition between jobs. This kept the expensive hardware busy, but it kept the people waiting. The second answer was multiprogramming, multiple programs in memory at once, with the processor switching between them when one waited for input or output. This used the hardware more efficiently, but people still submitted their work and waited for results. The third answer was time sharing, multiple users at terminals, each getting a rapid slice of the processor's time, each perceiving the machine as responsive and personal. This made computing interactive and transformed the relationship between people and machines. The fourth answer was the personal computer. Stop sharing the machine. Give each person their own. This seemed like it made the sharing problem irrelevant, but it brought the same problems back at a smaller scale, because even on a personal computer, multiple programs run simultaneously and share the same processor, memory, and storage. The fifth answer was the smartphone. Put the computer in your pocket. This brought the sharing problem into even more intimate territory, because now the operating system managed not just programs competing for processor time, but applications competing for battery life, screen space, network bandwidth, and access to the user's personal data. And the latest answer, in the world of servers and cloud computing, is virtualization and containerization. Share one machine among many virtual machines or containers, each one isolated from the others, creating the illusion of dedicated hardware on top of shared infrastructure. Each answer used the same fundamental tools: process management, memory management, file systems, scheduling, permissions, hardware abstraction through drivers. The tools were refined and extended with each generation, but the underlying concepts, the problems being solved, remained recognizable from one era to the next. There is something else running through this story that is worth naming explicitly, because it explains why operating systems look the way they do today. It is the idea of abstraction. An abstraction is a simplification that hides complexity behind a clean interface. The process is an abstraction. The running program does not need to know about context switches, scheduling algorithms, or processor registers. It just runs, as if it had the machine to itself. The virtual address space is an abstraction. The program does not need to know about physical memory, page tables, or swap areas. It just sees a large block of addresses, starting at 0. The file is an abstraction. The program does not need to know about disk sectors, block allocation, or journaling. It just opens a named file, reads from it, and writes to it. The device driver is an abstraction. The program does not need to know the specific commands for a particular brand of hardware. It just asks the operating system to perform an operation, and the driver handles the details. Each of these abstractions made programming simpler by hiding the complexity of the layer beneath, and each abstraction made it possible to change the underlying implementation without affecting the programs that depended on the interface. You can replace the physical hard drive with a solid-state drive, and the file abstraction keeps working. You can add more physical memory, and the virtual memory abstraction adjusts automatically. You can switch from one processor to another, and if the operating system and the compiler support the new processor, the programs continue to run. Abstraction is not free. It imposes overhead. The virtual memory system takes time to translate addresses, The file system takes time to manage metadata. Context switches consume processor cycles. Every abstraction layer between the application and the hardware adds a small cost. But the benefits are so enormous in terms of programmer productivity, system reliability, security, and flexibility that the trade-offs are almost always worthwhile. The history of operating systems can be read as the progressive construction of these abstractions, each one solving a problem that the previous generation of computing created. And the result is the computing environment you use today, where you can open dozens of applications without thinking about memory management, save files without thinking about disk sectors, and connect to the internet without thinking about network protocols, all because decades of people built the abstractions that sit between you and the hardware. Now let's follow a few more threads that run through this story, because they connect the past to the present in ways that are easy to miss. One thread is backward compatibility, the commitment to making new systems run old software. We saw this with the IBM System 360, where the decision to maintain compatibility created an architecture that lasted 60 years. The same tension appears everywhere in operating system design. When Microsoft built Windows 95, it contained code specifically designed to run programs written for MS-DOS and earlier versions of Windows. When Apple transitioned the Macintosh from Motorola processors to Intel processors in 2006, and then from Intel to its own Apple Silicon processors starting in 2020, it created translation layers that allowed old software to run on the new hardware, sometimes with remarkably little loss of performance. When Linux added new features, it followed a policy articulated by Torvalds himself. The kernel should never break the interface it provides to existing programs. Old programs should keep working on new kernels. Backward compatibility is expensive. It means carrying old code, old interfaces, old design decisions forward. Even when better alternatives exist, it constrains future design, because every new feature must coexist with every old one. It increases the attack surface for security vulnerabilities, because old code that is still present is old code that can still be exploited. But the alternative, breaking existing software and forcing users to replace it, imposes its own enormous costs. The entire ecosystem of applications, plugins, drivers, and tools that people depend on was written against the current interface, and breaking that interface means breaking all of that software at once. Every operating system designer faces this tension, and every major operating system has a different posture toward it. Microsoft has historically prioritized backward compatibility very highly, sometimes to the frustration of its own engineers who want to clean up old decisions. Apple has historically been more willing to break with the past, deprecating old interfaces and forcing developers to update their software, sometimes abruptly. The Linux kernel occupies an interesting position, with a very stable interface for programs running on top of the kernel, but relatively frequent changes to the internal implementation underneath. Another thread is the tension between openness and control. Unix was originally shared freely with universities, and that openness fueled its adoption and the development of a vast ecosystem. Linux went further, releasing the source code under a license that guaranteed it would remain free for anyone to use, modify, and redistribute. Android adopted a similar open source model, allowing any hardware manufacturer to use it. On the other side, Apple has always maintained tight control over its operating systems and the hardware they run on. iOS locks users into Apple's ecosystem, with Apple controlling which applications can be installed and taking a percentage of all sales through the App Store. Microsoft controlled the interface specifications that software needed to meet, though Windows itself ran on hardware from many manufacturers. These different approaches have produced different outcomes. Open systems tend to spread more widely because the barriers to adoption are lower. Controlled systems tend to provide a more consistent experience because one entity is making the design decisions and enforcing the standards. The debate between these approaches has been running for decades and shows no sign of resolving because both models have genuine advantages. A third thread is security, and it is worth following because the security landscape has changed fundamentally since the early days of computing. The first operating systems had no security at all. There was no need. The machines were physically guarded, the users were known, and the computer was not connected to any network. Security was a physical problem, keeping unauthorized people out of the computer room, not a software problem. Time sharing introduced the need for software security. Because multiple users shared the same machine,